Okay guys, so we're continuing the example that we had in the previous class. If you remember that we had this, look at here, we had a series of rotation and translational motion. So we said here is O naught, X naught, Y naught, and the Z naught. In the first transformation, we were rotating everything around the axis X. So here going to be X1. We having a previous notes. This is the example that we had. That's right. So for the angle of what? For the angle of alpha. So here we go. So here gonna be y1 and the z1. That's right. And the z1. Then we had a translational motion that we moved everything around the x-axis, right, for this distance. So here is going to be y2, z2, z2 and y2, and obviously x2. So this distance was how much? Let me look at the problem. A. That's right. Then for the third one, we wanted to move this coordinate system to here. I don't know. And having, see, here we go. That's right. So x3, z3 and y3 and y3 for this distance of how much? For this distance of actually here was B, guys, from the previous example. Here was, this distance was B. Let me change the color because here was B and this is A, for this distance of A. And the last one that we transformed was, let me do with orange. We were rotating around the new Z, right, for the angle of what? For the angle of theta. So this is going to be, and finally x4, right, x4 and y4. Right. So we want to see the homogeneous transformation that relates the fourth frame to the base frame. Right. So as we had in the previous class, I said because we are doing around the current axes, so we have to go forward. So the first was a rotation of what? X and alpha around the axis multiplied by translational of and the x and the distance b multiplied by again translational, right, around axis z, so z and how much? A, that's right, multiplied by again final rotational of current z and the angle of theta. So this is the homogeneous transformation that is connecting this coordinate system to the base coordinate system. So let us do one by one, right? So as you know, this is homogeneous transformation. Here we go. Here is 0, 0, 0, 1. We have only rotation, so the displacement or translation part is 0. So x1 respect x not gonna be 1 and 0, 0. Now you know it from rotation metrics. So y1 and here angle gonna be how much? Here angle is how much? Alpha, and this angle is alpha. So gonna be y1 with respect to x naught gonna be 0 obviously because it's normal. This gonna be cosine alpha and the sine alpha with respect to z naught. And z1 with respect to x naught again gonna be 0 because they are normal. So this is gonna be minus sine alpha and with respect to z naught gonna be cosine alpha. So we did for the first one. So this one, look at here. This is for this. Here we go. That's right. Now let's do the next. Next is only translation around the new axis. That's right. That x1 is on the x0 because we did the rotation on the x0. So again, so what we're gonna do again is this 0, 0, 0, 1. So here gonna be everything gonna there's no rotation. We're gonna have unity matrix here. That's right, because you see x1 is over x0. That's right. Sorry, y2 gonna be on x1, y2 gonna be parallel to y1, and z2 parallel to z1. So here only have along the x-axis, y1 axis, gonna be b0 and the 0. Understand? Now this multiplied by the third one. So let me re-emphasize again. This is for this part, right? Now 3 respect to 2, frame 3 respect to 2. So if you do that, gonna be 0, 0, 0, 1. But in the 3 respect to also is translational. That's right. This one is. So along which axis? Along the z-axis, z2 axis. So here gonna be 0, 0, and plus a, because going to the plus direction. That's right. No rotation. So again, you're gonna have rotation, unity matrix, right? Because x3 is parallel to x3 is equal to x2, y3 is equal to y2, and z3 is parallel to z2. So again, this is for this part. And finally, the fourth one, this. So finally, we have rotation around what? The z. So only have rotation. Again, gonna be 0, 0, 0, 1. There's no translation, 0, 0, 0. So rotation, so x4 respect to x3 gonna be again what? Cosine theta. I hope that you know it because I taught you many times. Respect to y gonna be sine theta 0, and the y4 respect to y3 gonna be minus sine theta cosine theta 0, and here we go. And obviously this is for this part. Understand? So the final result, if you multiply everything together, okay, so I did on the piece of paper, I have it here. So gonna be cosine theta minus sine theta 0 b cosine alpha sine alpha cosine alpha cosine theta minus sine alpha minus sine alpha sine alpha sine theta sine alpha cosine theta, if I'm not wrong, cosine alpha a cosine alpha 0, 0, 0, and 0. Sorry. Obviously this is wrong. Here must be 1. Okay, so let me go to the next page. Right, so now let us go to eventually to a real robotic systems. Okay, so for that, as you remember, I talked to the forward kinematics about the forward kinematics. When we have the, what was that? When we have the angles of the links, and based on that, we are determining the positional orientation of the end effector. But in inverse kinematics, we have to decide trajectory of the end effector, x, y, z of that on 3D space. Then, and having that, we're gonna determine the angles of the links. But now we are talking about the forward kinematics. So now look at this robot, guys. Look at this robot, a manipulator, like the one I have in the lab. That's right. So we have to fix your fixed coordinate system or frame, x naught, y naught, and that's right. And a link goes out of this joint, this vertical joint, and coming here. So this is gonna be z naught. That's right. I will teach you how to assign the coordinate system to a link. Okay. Then I have this joint, which is normal to the joint 0. This joint. Then a link goes here. Then I assign, let me change the color, a coordinate system to this link and joint. This link and this is joint, and this is z1 and the x1, and using the right hand rule, that's right, this is gonna be your y1. I will teach you eventually. That's right. So, and now again plotting the second joint that is parallel to joint 1. Here we go. Here we go. And then continues. So I'm assigning the, obviously like this, z2. I will teach you how to assign the coordinate system. Okay, don't rush. Only accept this from me now. And the y2. And then finally we reach to end effector. Suppose this is our end effector, so I'm gonna be z3 and the x3 and the y3. Here we go. So length of this joint gonna be L1, L2 and the L3. Okay. So there are some conventions that you have to know. I'm writing here. A manipulator with n joints has n plus 1 links, including base or ground, say. Okay, how many joints we have here? 1, 2, 3. Here we have 3 joints, so your n is 3. So based on whatever I said here, you're going to have 3 plus 1 what? Joints. They are the number of the joints. So let us count. 1, 2, let me do 1 joint, 2 joint, 3, and the fourth is the ground. That's right. The base. That's right. This is the ground. That's right. Understand? It's base. You can say this cube is attached to the ground. That's right. So this is one rule. So if you have n joints, you have n plus 1 links. Second that you have to know, we number joints from 1 to n and links from 0 to n. That's right, because you have n plus 1 link. That's right, but you have n joints. So this is joint 1, joint 2, joint 3. That's right. But when you want to name the links, let me change the color. Gonna be 0 for the ground or base, x naught, y naught, z naught. 0 for this joint 1, joint 2, link 2 and link 3. So link 0, link 1, link 2, link 3, joint 1, joint 2, joint 3. That's right. So now you have 1, 2, 3, 4 links, but 1, 2, 3 what? Joints, as this says. Clear? Now the other rule. Joint I, joint number I, connects links I minus 1 and I. This is joint 1. Joint 1 connecting the ground 0 to link 1. Joint number 2 connects link 1 to link 2. Joint number 3 connects link 2 to joint 3. Here we go. This is another rule. That's right. This is obvious. So when joint I is actuated, say, by a DC motor, link I moves. Okay, when joint I is actuated, link 1 moves, is rotating in this direction. When joint 2 is actuated, the link 2 moves, is rotating at this direction. That's right. When joint 3 actuated, link 3 moves, is rotating at this direction. Understand? These are very obvious. You can see from the figure. As I said previously, link 0 is base and fixed, as we know. Here we go. Understand? So book here, because it's gonna warm up and gonna freeze, and you're gonna send me email that what happened, right? So another thing, for joint I, we associate a joint variable, namely, I'm changing the color, QI. We say generalized coordinates. When I teach you about the Lagrangian equation to derive the dynamic equation of a robot, you'll understand. So QI for joint I, you have two types of that. One of them is for rotation, theta I. This is for DI that you have seen in the homogeneous transformations, right? Theta I for the revolute joint, means rotating joint. You have rotational motion, and this is for prismatic joint. When you have what? Based on the homogeneous transformation, translational motion. So this is, you can imagine this. This joint is this link is sliding on this link. So this is a prismatic joint. So here you have displacement. right? Oh, what happened? Okay, but for example, this is a what? A rotational joint, revolute joint, because this is rotating, so this link is rotating. Let me change the color to make sure when the joint I is actuated, the link I is moving. So when this is rotating, this link rotates. But when this joint is rotating, this link moves. That's right, based on whatever I said previously. We, after knowing this, we rigidly attach a coordinate frame. This is what, as I told you, coordinate frame means this, guys. See, this coordinate frame, x1, y1, z1, x. This is 2. I'm getting overs. x2, y2, z2, x3, y3, z3, x0, y0, z0. That's right. These frames. Coordinate frame to each link actuated by a joint, or simply for link I we assign a coordinate frame of OI, XI, YI, and the ZI, right? Look at here, guys. For link hold on, this is freezing. I don't know what happened. Okay, that's working. So for link actually this is okay, this is not good. This is not good expression, guys. Forget about this. Okay, it's gonna be confusing for you. So that's right. So but we know that for each link that is actuated by the joint, we are attaching a coordinate frame. That's right. Understand? Okay. So for link O, that's right, that is base, we attach X, O, Y, O, Z, O. So right, for link 1, we are attaching X1, Y0, Z1. That's right, and together. That's right. So obviously we have to do that. Okay. So this is very important, guys. What is that? Let me change that. When joint I is actuated, okay, link I and its attached frame OI, XI, YI, and ZI experience a motion, right? So like when we are rotating this joint by actuator, link 1 is rotating in this around this axis. When we are actuating this joint around the Z1 axis, this link is also what? Actuating. When we are doing this, this link is actuating. Understand what I'm talking about? So when we are actuating joint 3, link 3 is actuating. Joint 2, link 2 is actuating. Joint 1, link 1 is actuating. Understand? This is very obvious, like as your hand motion. That's right. So, okay. Okay. Now, after having these trivial conventions, okay, after having these trivial conventions, suppose AI is homogeneous transformation that I taught in the previous class, expressing the position and orientation, means rotation situation, of OI, XI, YI, ZI of a joint I with respect to OI minus 1, OXI minus 1, YI minus 1, and ZI minus 1. Okay? Okay, like this. Look at here, guys. Look at this robot. We have homogeneous transformation AI that express the orientation of this joint or attached frame to this joint, and this joint to this joint, and continues. Understand? So, when we name it as AI is a function of the coordinates QI. Understand? So, homogeneous transformation expressing both position and orientation of OJ, XJ, YJ, and the ZJ with respect to OI, XI, YI, and the ZI is called, I'm changing the color, transformation matrix and denoted by TJ with respect to I. From the beginning of this course, I said that the underscript respect to upper script. J respect to I, transformation matrix. Huh? So, and we are expanding mathematically based on whatever I taught previously. J with respect to I is equal to I plus 1, I plus 2, I plus 3, and Aj minus 1, Aj, if I is smaller than J. It must be, right? So, for forward kinematics that we're talking about is like that. So, example I just bring for you. Example, we want to find transformation matrix of example. If I give you a robot manipulator and say find the 3 respect to the 1, means transformation of coordinate frame 3 to respect to the 1. Where? In this robot. Here we go. Come on. Here we go. I want to find see 3, this frame that is located at the end effector respect to the 1. I want to find the transformation matrix of this. That's right, 3 this respect to this. Listen. Based on whatever we developed here, look at here guys. So your I is what? 1, your J is 3. So you're gonna say gonna be I will go, sorry. You're gonna be A 2 respect to 1, A 3 respect to 2. We can say 2 with 2 goes hell and get that, but we don't, that's right. So A 2 respect to 1, this is for work kinematics, look at here. When I find this one, 2 respect to 1, 3 respect with 2. That's right. So obviously you have to find the homogeneous transformation that I taught you one by one. So 0, 0, 0, 1. Okay, when we actuating this joint number 2, link to moves, that's right, but only we are subject to rotational motion. This is revolutional joint, that's right. So this link gonna only rotates, this gonna rotates up and down, that's right, because this is planar, it's going up and down, that's right. So we know that there is no translational motion. Yep. Now, so when we rotate this, here we go, we'll have 2 respect to 1. When we rotate this, that's right, this frame also rotates, that's right, but rotates but only x2 and y2 is changing because the z is the same, that's right, parallel to z1. So on the other hand, let me plot it here because I want to make sure that you understand. So see here, this is z1, x1, y1, and the original x2, y2, z2 was this, that's right. Let me plot it here, z2, x2, and the y2. Look at here. Original is that, but when you're rotating, this also is rotates, that's right. Also rotates. I'm going to talk about this just in a moment, that's right. So when this rotates, this gonna be like this. When it rotates, it's gonna be say rotating in this direction, say theta 1. So this is gonna be like this, right? Say x prime 2, y prime 2. Understand? Yes. Why is freezing? So first of all, let me change the direction of rotation. See, I'm in this direction. I'm gonna just respect to the right hand rule, theta 1. So here I'm gonna modify those. So if that happens, so you're gonna have this, right? X prime 2, y prime 2. So now you can simply say here is cosine theta 2, sine theta 2, theta 1, theta 1 and 0, right? Minus sine theta 1, cosine theta 1. Now you know this, and because the direction of the z doesn't change. But here we have 0 and 0 and 0. Obviously no, guys. Why? Because the origin of this has an offset or displace respect to origin of this for which length? Length of L2. So you have to be very careful, guys. So here you have, in which direction? In X direction. So L2, 0 and 0. Understand? Now let's go to the second one. A3 respect to 2. A3 respect to 2 gonna be exactly the same like this. So if you do that, 0, 0, 0, 1. So look at here, guys. Do we have translation on 3 respect to 2? Yes. Offset of L3 respect to the origin. That's right. So it's gonna be L3 again. Why in the X direction? This is X direction. L3, 0 and 0. And now the same if we rotate around I want to rotate around in this direction, say theta 2. Theta 2, you're going to have the same behavior. So you're going to have cosine theta 2, sine theta 2, and 0 minus sine theta 2, cosine theta 2, and 0, 0, 0, 0. That's right. And then you can get the answer. For the homework, see if you can find t of 2 with respect to the base 0. Find it for yourself. Okay. Obviously, this transformation matrix of I with respect to j is equal to I unity matrix if I is equal to j. For example, t of 1 with respect to 1 is I 4 by 4, or transform 3 with respect to 3, I again 4 by 4. No doubt. Understand? So again, guys, be very careful about this, because you have an offset of the origin of the frames. Understand what I'm talking about? So if I say, I want to just give you a valuable point here. So origin of this 1 with respect to the 0, what is the offset? Let me give you a hint. If you find the transformation matrix, I'm just giving you this part, 0, 0, 0, 1. So I'm talking about the 1 with respect to 0, frame 1 with respect to frame 0. So the origin of this with respect to this has offset of L1. In which direction? Z. So here you got to say 0, 0, L1. Remember, compare this with this. It's in the direction of LX, L2, 0, 0. Understand what I'm talking about? In direction of Z. So you have to be very careful when you are developing this. So for summary, before teaching you Dennett-Hartenberg parameters, we had DH parameters in robotics. So I want to just summarize everything. I'm gonna be enough for this class. So we say, so homogeneous transformation or rotation transformation matrix is gonna be R rotation matrix of frame n on joint n respect to base. So O n respect to base translation are 0 and 1. That's right. And we said that the H is equal to A1 to AN or T. That's right. And we know that AI, as we said that here, is again rotational matrix of I respect to I minus 1, O I respect to I minus 1, and the 0 and 1. This is the, this you can say, or T, transformation matrix. This is that compact version of what I covered in this class. So the other point is that why I changed the rotation of this joint from clockwise to counterclockwise because I want to respect the right hand rule. That's right. So if your thumb is in direction of the Z1, so theta 1 gonna be the right hand rule. But you can do in another fashion. Look at here. I said here theta 1. So here you have to change only the signs here. Look at here. And here gonna be your y2 gonna be positive and positive. Understand? If you change theta 1 is like this. So it depends how you do it. Understand? I want to be consistent with the right hand rule. Understand? So this is for this class. So the next class I'm gonna teach you DH parameters that you can find in any published articles in field of robotics.